Welcome, Mr. Sutton here with the BC Calculus 711 Part 2 homework solutions on direct comparison test. On this problem, we're trying to figure out the convergence of this series. Now this is one that's going to pass the nth term test, but there isn't really any other easy category this falls into, so we're going to try the comparison test on this one. Now this one is pretty close to the series 1 over n, which is the harmonic series which we know diverges. So is 1 over n bigger or smaller than this? Well, if we have a diverging series, we want to prove our diverging series is smaller than the other series. Because if you're bigger than a diverging series, it means you also diverge. So just comparing these things, 1 over n, the only difference between this and the original series is you have this 1 in the numerator. 1 is going to be smaller than ln of n, at least for certain n values. So I'm going to write 0 less than or equal to 1 over n, less than or equal to ln of n over n. And this is going to be true if you have an n value of at least 3. It starts being true when n equals e, but after e, certainly, this is true forever. So since we have a series that is bigger than another series that diverges, that means our original series must diverge by the direct comparison test. On this problem, we want the convergence of this series right here. Now, this one is going to pass the nth term test, and there isn't really any other easy category it falls into, but n over n cubed ought to behave pretty similar to 1 over n squared. This plus 1 really shouldn't make a huge difference for convergence. So I'm going to compare this to n over n cubed without the plus 1 down there, and we know that we can reduce this to 1 over n squared. Well, 1 over n squared, that's going to be a p-series with a p-value of 2. And since 2 is greater than 1, we can prove that this is going to converge by the p-series test. All right, let's compare this series with the original. Now, the only difference here is that we have an n cubed plus 1 in the original, which is going to make the original smaller, because you have a larger denominator, than this comparison series. So I can write 0 less than or equal to my original here, which is less than or equal to this n over n cubed comparison series, which is equivalent to 1 over n squared. Since we have a series that's less than another series that converges, that means our original series also converges. And again, I'm just going to write my n values here. So this is going to be true for n greater than or equal to 1. So since we're less than a converging series, this series converges by direct comparison test. On this problem, we want convergence for this series. Now this one is going to pass the nth term test. The nth limit is going to be 0. So we move on to some other tests. And we see that this is actually pretty close to a geometric series. Not quite there because of this plus 1, but it ought to behave similarly to the series 3 to the n over 5 to the n. So we're going to compare this to the series 3/5 to the n, which we know is a geometric series. This has a common ratio of 3/5. Absolute value of that is 3/5, and that absolute value is going to be less than 1, which means this comparison series converges by geometric series test. So comparing this now to what we started with, the only difference really when you get down to it is the original has a larger denominator, which makes it smaller than the comparison series. So we can write 0 less than or equal to 3 to the n over 5 to the n plus 1, less than or equal to our comparison series of 3/5 to the n. And this is going to be true actually immediately at n equals 0. At 0, you've got 1 over 2, which is going to be less than or equal to 1, which is what this stuff comes out to when you plug in 0 for n. So this is true for n greater than or equal to 0. Since we've shown that our original series is less than a converging series, that means our original converges by the direct comparison test. For this problem, we're trying to figure out convergence for this series. Now this one is going to pass the nth term test, which doesn't really help because a lot of diverging ones pass, but factorial is such a fast-growing function, I'm pretty sure this one is going to converge. We just have to prove it. The fastest way to prove it would be with a comparison to another series that converges, such as 1 over n squared. I could use 1 over n factorial, but then proving 1 over n factorial converges takes a little while. 1 over n squared is pretty easy. This is a p-series, p-value of 2. Since that's greater than 1, we already know this is going to converge by the p-series test. Comparing these now, this faster growing denominator is going to give me a smaller overall fraction than 1 over n squared. So I can write 0 less than or equal to this original series, nth term, which is going to be less than or equal to 1 over n squared. The only thing you have to be careful about when you're using functions that are not very similar in a comparison test is making sure the inequality is actually true for those lower n values. I mean, we know factorial eventually outstrips polynomial growth, but in the beginning it may take a while for it to get going. So let's just look at n equals 1 and make sure this inequality is actually true for that. If n equals 1, we have 1 over, let's see, 2 times 1 plus 1 is 3 versus 1 over 1, so that's true. If n equals 2, we have 1 over 5 versus 1 over 4. If n equals 3, we have 1 over, let's see, 2 times 6, so 12 plus 1 is 1 over 13 versus 1 over 3 squared, 1 over 9. So yeah, this is going to be true for n greater than or equal to 1. So since we have a series that is smaller than another series that we know already converges, our original series must also converge by the direct comparison test. For this problem, we're trying to figure out if this series converges absolutely, conditionally, or not at all, with reasons. Since this is an alternating series, it's probably going to converge, but let's test out the absolute case before we test out the conditional case. So let me consider this series without the alternating. So absolute value would just give us 1 over radical n minus 1. And now this is pretty close to a p-series. I know it's going to go to 0 by the nth term test, but this is pretty close to 1 over radical n, so I could use a comparison test with 1 over radical n to see what's happening with this thing. So let me do that. I'll compare this to 1 over radical n, which is a p-series with a p-value of 1/2. Since 1/2 is less than or equal to 1, we know our comparison series diverges by the nth term, or the p-series test. Comparing it to the original now, this original, it has a smaller denominator, which makes it bigger overall than our comparison series. So the order in our inequality, we can say 0 is less than or equal to our comparison series, which is less than or equal to 1 over radical n minus 1. What n values is this true at? Well, if I plug in 1 for n, I've got 1 over 1 versus 1 over 0. That's no good. So let me make it n equals 2. 1 over radical 2, which is 1 over something bigger than 1, that is going to be less than or equal to 1 over 1, and that's going to continue being true. So I need to make my n value 2 or greater so that I, at the very least, don't have an undefined in one of these. Next, since I have a series that is bigger than a diverging series, that means my original is going to diverge by the comparison test, the direct comparison test. But this is just the absolute value version of the series. We still have to test the original series with the alternating thrown in. Now this original series here, we see alternates, and since I have a denominator that's growing, this is going to decrease in value to 0, in absolute value to 0. So since the terms of the original alternate and decrease in absolute value to 0, that means this original is going to converge by the alternating series test. And it's going to converge conditionally because it only converges without the absolute value. For this problem, we want to know if this series converges absolutely, conditionally, or not at all. And we have to ask about the whole absolute versus conditional thing because sine of 4 is actually a negative number. It's a little bit more than sine of pi, so it's below the y-axis. And we keep raising it to different powers, so this is going to keep alternating back and forth between negative and positive, and maybe not in as predictable a pattern as we like anyway. So I'm going to start by considering the absolute value version of this series. So I'm going to write absolute value of sine of 4 to the nth power over 2 to the n squared. And I'm pretty sure this one is going to converge because sine of 4, raising it to these different powers, is never going to be any bigger than 1. So for all intents and purposes, this numerator isn't really growing. The denominator is growing, and it's growing at a pretty good pace either by p-series or geometric series standards. So I'm just going to pick a comparison series that shows that this thing is converging. So I have a choice between really 1 over n squared versus 2 to the n. 2 to the n is a faster growing denominator, so I'm going to pick that for my comparison. So I'm going to compare this to 1 over 2 to the n, which is a geometric series with a absolute value common ratio of 1/2. Since that is less than 1, I very quickly show that my comparison series converges by the geometric series test. Now comparing that to the original here is going to have no bigger than 1 for a numerator, and the denominator is bigger because you've got this n squared to go with the 2 to the n, so that actually gives you a smaller overall fraction. So I can say that 0 is less than or equal to my original, which is smaller than or equal to this comparison series of 1 over 2 to the n. And this is going to be true for n values really starting pretty much immediately at 1. Immediately at 1, this is going to be true. So going ahead then, I've shown that my series is less than a converging series, so the original then must converge by the direct comparison test. And since the absolute value version of this converged, that means that we're going to converge absolutely by the direct comparison test. On this problem, we're trying to evaluate the following statements about convergence for the series 1 over ln of n plus 1. So taking a look at these, they all talk about comparison, so we're going to be using a comparison test. And we've got converging versus diverging, and really only two comparison functions, 1 over n and 1 over n squared. Well, we know 1 over n is going to diverge, so you'll never be able to prove convergence using that. So choice A is probably garbage. And we know that 1 over n squared converges, so you're not going to be able to prove divergence with a converging series. So choice D also can be eliminated. So it's down to B or C. So let's go through and actually do the comparison test for this. Since we have to choose between 1 over n and 1 over n squared, we have to figure out kind of in advance whether we think this thing is going to converge or diverge. Since ln is such a slowly growing function, I'm thinking this is going to diverge. I don't think this is slowing down fast enough to converge. So I'm going to compare it to 1 over n because I know that diverges as well. So we'll compare it to a series of 1 over n, starting at 1 going to infinity. This is the harmonic series, which we know diverges. So we also know that 1 over n is actually a faster growing denominator than ln of n plus 1. So this is actually going to be a smaller series than the original. So I'm going to write 0 less than or equal to 1 over n, less than or equal to 1 over ln of n plus 1. And that's going to be true for all values 1 and greater. So this means that since my series is bigger than a series that I know diverges, my original series must also diverge by the direct comparison test. So this is going to be, let's see here, answer choice C, diverges by comparison with 1 over n. For this problem, we're given 3 different series, and we're asked which of these converge, and it could be more than one of them. So we just have to go through each of them and see if it converges or diverges. For option 1 here, we have 4 over the square root of n. Now that's pretty similar to 1 over the square root of n, which is a p-series that we know diverges. So you could use a comparison test to prove that option 1 diverges, but a faster way to do this would just be to pull this 4 out of the summation, since it's just a constant being multiplied by the summand. So I'm going to just rewrite this one as 4 times the series 1 over radical n. Now this series in here I know is a p-series with a p-value of 1/2. Since that's less than or equal to 1, that means this is going to diverge by the p-series test. And if I have 4 times something that's diverging, that's still going to diverge. Moving on to the next one. This next one is actually a geometric series. ln of 4 is a constant being raised to an exponent. So since that's geometric, we look at the common ratio, which in this case is 1 over ln of 4, and that's the absolute value of the common ratio. ln of 4 is a number that is bigger than 1, because ln of e would be 1, and e is about 2 point something. So I'm dividing 1 by something bigger than 1, which means the overall result is something that is less than 1. Since we're less than 1 by the geometric series test, this is going to converge as well. So moving on then to option 3, we've got 1 diverging, 1 converging. Option 3, well, this one I notice is an alternating series, and the denominator is growing, so this is an alternating series with terms that are decreasing in absolute value to 0. Well, that means that this is going to converge by the alternating series test. So in the end, only options 2 and 3 are going to converge, which gives us answer choice E. For this problem, we're given that B is less than A, and both of these are positive series for n greater than or equal to 1. So we want to know which of these statements has to be true based off of this. Well, whenever I see this kind of reasoning with this three-sided inequality and comparing things, I think comparison tests. And when we're talking about one of these converging and the other diverging, again, I'm thinking a comparison test. So let's see what the direct comparison test says about this situation, and then we'll analyze these different options. So one thing the direct comparison test says is that if A converges, if a larger series converges, then anything smaller than that, like B, will also have to converge. And going the other way, if we have a smaller series like B that diverges, anything bigger than that, like A, will also have to diverge. So taking a look at some of the answer choices here, answer choice A, the nth term of A goes to 0 as the limit approaches infinity, and they're saying we can conclude from that B converges. Well, if the A series passes the nth term test, it might converge, and if it converged, B would also have to converge since B is smaller than A. However, the fact that you pass the nth term test, that the limit of your nth term is 0, is not enough to prove a series converges. A might converge, it also might diverge. The harmonic series passes the nth term test as well. So we can't actually pick A because we don't have enough to prove that A converges, so we can't then prove that B converges. Moving on to answer choice B. If A converges, then the limit as n approaches infinity of B is 0. Okay, well, if A converges, then that means that B must converge. If B converges, is it true that the limit of the nth term is going to be 0? Well, yes, it is, because every converging series passes the nth term test. Passing it is not enough, but it's at least a requirement for convergence. So we actually can pick choice B. Let's just take a look at the other ones, though, to make sure we can really eliminate them. Choice C, if B diverges, then the nth term of A is going to be 0. Well, if B diverges, that means that A is going to diverge. Now, if A diverges, it could have an nth term test that comes out to 0, like the harmonic series, or not. It could go either way. It could actually fail the nth term test on the first try. So C isn't necessarily true. Choice D, if A diverges, B diverges. Well, A is bigger than B, so the fact that A diverges tells us nothing about a smaller series. And then choice E, if B converges, A converges. B is smaller than A. The fact that a smaller series converges doesn't tell you about a bigger series. So in the end, choice B is the best option. For this no calculator free response, we're given a Maclaurin series for the function f as this series right here. For our first task, we want the interval of convergence for this series. Since this is not geometric, we're going to have to use the ratio test. So I'm going to set up the limit as n approaches infinity of absolute value of, and now I have a big old fraction with n plus 1th term over nth term. So the n plus 1th term is going to be 2x to the n plus 1 over n plus 1 minus 1, so just n for that. And I can forget about this negative 1 because I've got the absolute value here to help me. Now for the nth term, that's just 2x to the n over n minus 1 down there. Same change flip. In my numerator, I've got 2x to the n plus 1 and n minus 1. Denominator now is going to have the n and the 2x to the n. I can reduce these 2x to the exponent terms by subtracting the exponents. So n plus 1 minus n just gives us a 1, so 2x to the 1 in the numerator, along with the n minus 1 that's already there. Denominator, well, all that's left over is this n, because we canceled out this 2x to the n completely. Next, as n approaches infinity, this minus 1 can be ignored. So we have a n over n, which just comes out to 1, and we still have this 2x acting as a coefficient. So we end up with 2x in absolute value then as the final result of this. So to get my interval of convergence, I'm going to set this less than 1. And then I'll just divide by 2 right away here, so I have absolute value of x less than 1/2. I can rewrite this without the absolute value as negative 1/2 less than x less than 1/2. And I'm going to put a question mark there because this may or may not be the final interval of convergence. We have to test the endpoints since we just used the ratio rather than the geometric series test to come up with this. So testing the endpoints now, at x equals negative 1/2, what series do we have? Well, if I plug in negative 1/2 for x, 2 times negative 1/2 is just negative 1. So we have negative 1 to the n times another negative 1 to the n. Merging the bases together, we end up with just 1 to the n, which is going to end up giving me, let's see here, well actually, yeah, that's just going to be 1. So we have 1 over n minus 1. Now this is pretty close to the harmonic series. So I'm going to compare it to the harmonic series. The harmonic series we know diverges because it is the harmonic series. Now the harmonic series is smaller than our original series. Our original series, we're subtracting in the denominator. That makes the denominator smaller, which makes the whole series bigger. So we can say 0 less than or equal to 1/2 less than or equal to 1 over n minus 1. And I'm going to say this is true for n greater than or equal to 2, because if I let n be 1, then we have 1 over 0, which is no good. So we'll start at 2, and this is true for everything 2 and afterwards. 1/2 is less than 1, 1/3 is less than 1/2, and so on and so forth. So we can then say that this series here, this incarnation, is going to diverge by the direct comparison test. So a lot of work to prove that we actually had the right kind of inequality on that endpoint. Let's check out our other endpoint now, 1/2. Hopefully this is a little easier. So if I plug in 1/2 for x, then I have 2 times 1/2, which is just 1. So 1 to the n, we can just ignore that. That just goes away. So we really just have then negative 1 to the n left over up there over n minus 1. Now this one is definitely a little bit easier. We know that this alternates. Since my denominator is growing while the numerator really isn't, we also have a function that is decreasing in absolute value to 0. So if our terms are alternating and decreasing in absolute value to 0, we've already shown then that this is going to converge by the alternating series test. So at the end of the day, writing our final interval of convergence, and I'll write it up here because, well, there's no room anywhere else, we had the right inequality for the first one. We have negative 1/2 less than x. And then for the next one, this should be x is less than or equal to 1/2. For this problem, our task is to show that y equals f of x, basically this series here, is a solution to this differential equation, and also that the radius of convergence for x is the same thing that we got from part A. So there's a lot of work to do on this one. First thing we need to do is figure out what the y function actually looks like and show that it comes out to this 4x squared over 1 plus 2x when all is said and done. So let's start by writing out the y function. So that's going to be, let's see, what we get when we plug in some numbers to this series up here. So let's start with 2. If I plug in 2, this is going to become a positive, and then this is going to be, let's see here, 2x quantity squared, so 4x squared over 2 minus 1 is just over 1. So 4x squared then is our first term. And then for the next term, if I plug in 3, now it's negative. Now we're dividing by 2. And up here, this is going to be 8x cubed. Well, 8x cubed over 2 is just 4x cubed. Next, if we plug in 4, this becomes positive. We have 16x to the 4th over 3. And then let's write out another one here. If we plug in 5, this becomes negative. We've got 32x to the 5th over 4. That's 8x to the 5th. And so on and so forth. All right. So now we're going to do some transformations on this. The next thing we're going to do to this series, now that we've written out, is we're going to prime it. We're going to see what y prime looks like. So going through and just taking the derivative of each term individually, we've got 8x minus 12x squared, using our power rule here. And then, let's see, this is going to be 64 over 3x to the 3rd. This is going to be minus 40x to the 4th, and so on and so forth. Next, to simulate the stuff on the left side of this differential equation, we need to multiply all this by x. So this is going to be xy prime. So that's going to be 8x squared minus 12x to the 3rd. So this one isn't so bad. 64x to the 4th over 3. And then finally minus 40x to the 5th, and so on and so forth. Finally, we have to subtract y from all this. Well, here's the y series up here, so let's just go term by term and subtract. So we're now doing xy prime minus y. So we've got these terms minus all these terms. 8x squared minus 4x squared is going to give us another 4x squared. We have a negative 12x cubed minus negative 4x cubed. So we're actually adding 4x cubed to get negative 8x cubed. And then we've got 64x to the fourth over 3 minus 16x to the fourth over 3. Well, that's going to be 48x to the fourth over 3, which we can reduce to just 16x to the fourth. And then finally, negative 40x to the fifth minus negative 8x to the fifth. So we're adding 8x to the fifth to get negative 32x to the fifth. And we could keep going. So now we have to show that this is equivalent to 4x squared over 1 plus 2x. Well, let's take a closer look at this. If you look at this for a little bit, you might notice there is a definite pattern here. We've got 4, negative 8, positive 16, negative 32. So we're multiplying by negative 2 each time to get the next term. We're also multiplying by an x to get the next x part of the term. So this is actually a geometric series. We have a starting value of 4x squared, and we also have a common ratio in our value of negative 2x. Well, it turns out that if we have these two things, we can write the sum of an infinite geometric series. That's the a1 over 1 minus r formula you may remember. So we can actually rewrite this whole thing as 4x squared over 1 minus negative 2x, or 4x squared over 1 plus 2x, which is exactly what they told us to prove this thing was equivalent to back here. So we've done this part of the problem. Now, to actually show this business about the radius of convergence, because we have to show this as well, we take the common ratio, negative 2x, the absolute value of that, and we're going to set that less than 1. And now to get the ratio, or the radius of convergence, we just get it so that it's 1x plus or minus something with something else on the other side of this less than. So basically, we have to divide by 2. So we have absolute value of x less than 1/2. This proves we have a radius of convergence of 1/2, which matches the radius of convergence on part A. Part A, remember, it was negative 1/2 to positive 1/2, so that was also a radius of convergence of 1/2.